Section 4.4, concavity and the second derivative test. How fast does the flu spread? This question is rather appropriate for what's going on right now. So a single person contracts the influenza virus or some other virus, and now the flu epidemic is spreading through Calculopolis. The number of infected people T days after the initial outbreak can be modeled by this function. The population of Calculopolis is 1,000. And the graph of the growth is shown. Number 1, describe how the number of infected people changes over the 21-day period. Well, we can see that we start with one person, and it starts to spread slowly at first. Then we can see that the spread takes off and there's rapid growth in the number of infected people, and then it starts to slow down again. That rate of change slows down by the end of the 21 days, probably because almost everyone at that point had gotten the flu. So what is the number of people infected growing the fastest? And how do you know? So pause the video if you want. Let's look at this graph. And the number of people infected would be growing the fastest when the slope is the steepest. And if we look at the slope in each of those boxes, it appears as though the slope is fastest, the steepest, between days 11 and 12. Remember that if the slope is the steepest, the slope is the first derivative. If the slope is the steepest, it's the biggest, f prime of t should be a maximum. Now I want you to go ahead and fill in the table with f prime of t and f double prime of t at those selected values. I'm going to go ahead and fill in this table. I basically used my graphing calculator, and if you need a reminder on how to do that, you should definitely come to class and ask that question, and we can go over that. Now I filled in the values for the first derivative, and I want to pause a second to take a look at what's happening. What is happening? Remember, the first derivative is the slope. So what is happening to my slope? It's getting bigger and bigger. It's getting steeper and steeper. But what happens between 11 and 12? From 11 to 12, now it's still a positive slope. It's still increasing, but my slope now is not increasing as fast, which means it had to have hit a maximum somewhere between 11 and 12. So I'm going to go ahead and, again, put that original function in my graphing calculator, and I can find that maximum. So there, the maximum is 150.75, which is, in fact, between 147 would have reached a max and then gone back down to the 146. Now I want you to go ahead and try to find the second derivative, the values of the second derivative at those exact same points, and let's see if we can see a pattern in the second derivative. So now these are the values that I have for my second derivative, and let's take a look at what's happening. So my second derivative, remember, is the slope of my first derivative. So as my first derivative is increasing, my second derivative has a positive slope. If we remember, between 11 and 12, my first derivative reaches a maximum, which means after 11.454, my first derivative is starting to decrease, which means my second derivative is going to be negative because my slope of my first derivative is going down, so it's a slope of 0. What happens at that peak? What do you suppose is the second derivative when my first derivative reaches a peak? Well, if we remember, since it reaches a peak, it's positive on one side and then it becomes negative on the other side, which means my second derivative is going to be 0. I have this little side note here, but remember, if f is increasing, then the derivative would be greater than 0. So therefore, we can just translate that kind of down a level or up a level. If f prime is increasing, then f double prime is going to be greater than 0. If f prime is decreasing, then f double prime is going to be less than 0. We basically have already answered number 4. For which values of t is f prime increasing? Well, f prime is increasing from 0 all the way up to 14.454, and then my f prime from 150 is decreasing. So from 11.454 to 21 days, it would be decreasing. Well, then I'd like you to pause the video and write down how both of those statements reflect in the second derivative. What does that mean in terms of the second derivative? Remembering again that the second derivative is just the slope of the first derivative. So if the first derivative is increasing, the slope must be positive. If the first derivative is decreasing, then the slope must be negative. How could we get this answer in question 4 simply by looking at the graph of f of t? Well, from the time of 0 to approximately 11.454, the graph is concave up. In other words, it's increasing at an increasing rate. And from 11.454, the peak of the first derivative, to 21, f of t is concave down, so it's still increasing, but it's increasing at a decreasing rate. Now let's put together a couple of these important ideas of the second derivative test. To begin with, basically, the second derivative tells how the first derivative, the slopes of f, are changing. If the second derivative is greater than 0, that means that the first derivative, the slope of the first derivative, is increasing. And this in turn means that the original function is concave up. On the other hand, if the second derivative is less than 0, then this is going to mean that f prime of x is decreasing, which in turn means that the original function is concave down. The second derivative test. First and foremost, the function must be continuous on the given interval. So your first step is going to be to find the first derivative and also all the critical numbers. Remember, the critical numbers are where the first derivative is either equal to 0 or undefined. Next, you're going to find the second derivative and all the inflection points. This is going to be where the second derivative is either 0 or undefined. An inflection point is where the graph of the function changes from being concave up to concave down, or from concave down to concave up. Third, you're going to make a labeled sign chart, just like we did with our first derivative test, and you are going to put on that labeled sign chart your inflection points as well as your critical points. Then you're going to plug those critical points into your second derivative and determine the value, whether it's positive, negative, or 0. If the critical value is negative, then the interval is going to be concave down, and that critical value is going to be a relative max. When you plug the critical value in, if you get a positive value, then that means that interval is concave up, and that critical value is a relative min. If when you plug the critical number in you get 0, that means that your critical number is also a possible inflection point. You can still use this to determine the concavity on each side of that value, but you would have to use the first derivative test to determine any extrema. Now let's use the second derivative test on this function in number 1 to find all relative extrema and to discuss the concavity of the graph. So I'd like you to go ahead and pause the video and at least do steps 1 and 2. Finding my first derivative, factoring it, and finding my critical numbers. I have my critical numbers are 0 and 4. Now my second derivative. Finding my second derivative and setting that equal to 0, a possible inflection point is positive 2. Now I'm going to make my signed line chart. I'm going to put my inflection point in the middle, and then on each side I have my critical values. And this is my second derivative test, so I'm going to let myself know that that's what it is. Now I'm going to plug 0 into my second derivative. When I plug 0 into the second derivative, I get a negative value over here. So that means that this is going to be concave down. When I plug in 4, 24 minus 12, I get a positive value over here. That means that this is concave up. So therefore, I can say that it is concave down on the interval from negative infinity to 2. It's concave up from 2 to infinity. I can also say that there's a max at 0. When I plug 0 into my original function, I get 0. And there's a relative min at 4. When I plug 4 into my original function, I get negative 32. So there I've discussed the concavity, and I've found all of my relative extrema. Example 2, they're just giving us the second derivative, and it wants to know for which values of x does g of x have a point of inflection. So again, we're going to determine that our possible inflection points are x equals 3, x equals negative 4, and x equals 6. Go ahead and make a labeled sign chart. If I then plug in values from each of these intervals, if I plug in a value that's less than negative 4 into my original function, I'm going to get, or into my second derivative, I'm going to get a positive number. that means that this interval is concave up. If I plug a number in between -4 and 3, so if I plug in 0, I get a negative. If I plug a number in between 3 and 6, I also get a negative. And if I plug a number in between 6 and infinity, I'm going to get a positive. And actually, I misspoke back here. This is going to be concave up because on each side of 4, it changes sign. If you notice on 3, it doesn't change sign, but from 6 it changes sign. So this is going to be all concave down, and this is going to be concave up. Therefore, my possible points of inflection, it changes from being concave up to concave down at 4, and it changes from being concave down to concave up at 6. So my points of inflection are going to be -4 and 6. The graph of f of x is shown. Determine the intervals where the first derivative is positive, that means the slope is positive, and the second derivative is negative, which means it's concave down. So where is it both increasing and concave down? So the function has a positive slope from a to c. It's concave down from b to d. Therefore, both of those things occur in the interval of b to c. Next, multiple choice. For the twice differentiable function, it is known that the first derivative is equal to 0 at 3. The second derivative at 3 is -1.5. Which of the following could be false? It's concave down. Well, the second derivative is negative, so this is true. It has a critical point at x equals 3. Well, the first derivative is 0, so this is true. It has at least one point of inflection. Can't really determine that. And it has a relative maximum at 3. So by the second derivative test, this is true as well. So by a process of elimination, C has to be the false one. And our last problem, just like the first one, use the second derivative test to determine all relative extrema and discuss the concavity. Again, pause the video and find your first derivative, critical values, and your second derivative and inflection points. Finding and solving the first derivative, I find that I have a critical number at -1. Finding and solving the second derivative, I find that my possible inflection point is also at -1. So now we're going to do our second derivative test with -1. So because my inflection point is also a critical value, I'm not going to be able to use the second derivative test to be able to find any relative extrema, but I can use it to find the concavity. So if I take a number that's less than -1 and plug it into the second derivative, I'm going to get a negative value. That's telling me, whoops, it's not telling me anything yet. If I plug in a number that's bigger than -1, I'm going to get a positive value. So this is telling me that it's concave down on that side of -1, on the left side, and it's concave up on the right side. So I can determine my concavity. I'm not given a closed interval, so it's concave down from -infinity to -1, and it's going to be concave up from -1 to +infinity. Now that I've determined the concavity, I need to determine if I have an extrema. So now I'm going to plug in, again using the first derivative test, so I'm going to plug in a number that's smaller than -1 into my first derivative, and when I do that, I'm going to get a positive number. When I plug in a number that's bigger than -1, I also get a positive number, which means this function is increasing the whole time. There is no decreasing. Since it doesn't increase and then decrease, there is no relative extrema. No relative extrema. And that concludes our notes for the second derivative test in section 4.4. Please make sure you come to class if you have any questions.